We're going to look at section 5.2. Primarily what we're doing in 5.2 is just going to be an extension of what we've done in chapter 5. Okay, so the foundations of what we're doing were what we did in chapter 5, or I'm sorry, chapter 4. So we'll kind of start with a little review of kind of what we did in chapter 4 and show you how we're going to kind of extend from there here in section 5.2. Okie dokes. All right. So in chapter 4, we did things like find the exact value of sine inverse 1/2 without using a calculator. So when you hear exact value in trigonometry class, what tool do you expect to be using? Unit circle. So remember, for sine inverse, our fundamental range was negative pi over 2 to positive pi over 2, which means that we're looking in quadrants 4 and quadrant 1. So we'll go to the unit circle and look for where y is equal, the y coordinate is 1/2. Why am I looking at the y coordinate? Because it's sine, exactly. Sine is all about the y coordinates. So I'll go over and I'll look at my unit circle, and I'm just looking in quadrants 1 and 4, and the only place where I see a y coordinate of 1/2 is right there, which tells me my answer should be pi over 6. Everybody feel okay? Remember doing that? Okay, and then we went ahead and said, okay, what if we give you an equation now, like sine x equals 1/2, and we tell you we're looking for our solution on the interval from pi over 2 to pi over 3. So we use that interval to figure out that that's talking about quadrants 2 and 3. So then we go to the unit circle, we look for where y is equal to 1/2 in quadrants 2 and 3. So if we did that, that's the only place in quadrants 2 or 3 where y is 1/2. So my answer would be like 5 pi over 6, right? Okay. What if now we give you the same question, but we've left off the interval, right? Notice we're not asking for values between specific angles. Could be any angle. How many answers am I gonna have for this equation? More than 2, more than 4, more than 12. Infinitely many. Why? Why is it going to be infinitely many? Yes, exactly. So for example, if we know pi over 6 is a solution to sine x equals 1/2, then any angle coterminal to pi over 6 would also be a solution. How many angles are coterminal to a given angle? Infinitely many. Now don't confuse this with all real solution or all real numbers being a solution, right? There are infinitely many solutions, but they are not anything as a solution to this. The things that work, there's just infinitely many of them, but not everything works. So far, so good? So we know that pi over 6, and anything coterminal to pi over 6 is a solution, right? So rather than writing that with words, what we're going to do is write it with symbols. So to write everything coterminal to pi over 6 with symbols, we write plus 2 pi k, comma, where k is an integer. So that stuff at the end is just mathematics symbols that means everything coterminal. So far, so good. And then similarly, from the previous question, we also know that 5 pi over 6 is a solution. Is pi over 6 and 5 pi over 6 coterminal? Are those two angles coterminal? No. How do you know? The difference between them is not a multiple of 2 pi, right? So that's another unique set of solutions. So we'll say 5 pi over 6 and then everything coterminal to 5 pi over 6. Does that feel okay there? So very much the same process as before, right? But now you're going to hunt the entire unit circle and then just put plus 2 pi k, k an integer after everything you find. No big deal, right? So far, so good? Okay. So let's make another version of this same question. What if we want to solve the equation sine x equals 1/2, but the interval that we're solving over is now 0 to 2 pi. Notice the size of this interval is bigger than 180, right? Previously, the size of our intervals had always been 180 degrees or pi units long. When we're in chapter 4, you guys remember that? Here we're going to look at, okay, what if that interval is bigger than pi, right? If we're going from 0 to 2 pi. So again, what we'd be doing is looking at the whole unit circle now at just where y equals 1/2. So I notice there's two such locations, pi over 6 and 5 pi over 6, right? So far, so good? Now, alternatively, the infinite solutions can also generate these answers. So for example, if we just let k equal 0, we'd have x equals pi over 6 plus 2 pi times 0, which is pi over 6. That's in between. And then if we say x equals 5 pi over 6 plus 2 pi times 0, that's also in between. Any other value of k that we pick, though, is going to either be too big or too small. Is going to result in an angle too big or too small. So another way of generating these solutions is just to find the infinite and use that as like our answer generator. We can just keep picking values for k until we've exhausted the things that fit in the given interval. Right? If I pick k equals -1, all my answers will now be negative. That's going to be too small. If I pick k equal to be +1, well, all my answers will be bigger than 2 pi, so they'll all be too big. The only answers that are going to fit from 0 to 2 pi were from k equals 0. So far, so good? So that's like our first major extension from what we did in chapter 4 was, okay, we can start talking about solutions where there's no interval given, where we can have infinitely many solutions. And then the second extension is, if we have our infinite solution, we can use that to generate solutions over intervals of any size, right? They don't have to just be pi sized like we did in chapter 4. They could be as big or, as big as you want them to be. Oops. The next extension that we're going to have is, what if our equation doesn't have the trig function all by itself on the left-hand side, right? In the previous chapters, we always had like cosine x equals 1/2 or something all by its lonesome on the other side. Here we're going to start seeing problems where you might have to do some algebra first before you're ready to go to your unit circle. So the only time we can go to the unit circle is when we have the trig function all by itself on the left-hand side of the equation. That means no coefficients, nothing added or subtracted, no exponents. So if I look at this equation, is the trig all by itself? No. What's wrong with it? It has an exponent, right? So my first order of business then is going to be to cancel out that exponent. What do I need to do to both sides of this equation to cancel out that exponent? Squaring cancels a squared? So if okay. What? Square root, right? That's, I think, probably what you meant. Okay. When we square root both sides of an equation, what do we have to remember to do? Okay. When we square root both sides of an equation, what do we need to remember to do? What? Nope. I mean, the square root of 1 is just 1, right? What are we forgetting? Plus or minus. Yes, when you square root both sides of an equation, that always is going to generate a plus or minus. Please don't forget that. So when I see a plus or minus, how do I what do I do with that? Well, I'm going to break it into two equations, right? That says that cosine x could equal 1 or cosine x could equal -1. Now that I have the trig function all by itself, I can go to the unit circle and look for where x is equal to 1. So I'll go back to my unit circle. Look for where x is equal to +1. I see it here at 0. Checking my x's. Oh, that's -1. That's not what we're looking for. We want +1 right now. Checking my x's. So it doesn't happen again until I've gone all the way back around to 2 pi. Everybody agree? Is 2 pi a viable answer? Well, let's look at the interval. Oops, that's not the question we're on. This is the question we're on. What does the parenthesis mean? it means it doesn't include it. The bracket is including, the parenthesis is not. So 2 pi should not be listed. So I have just x equals 0. So far, so good. Now I'll do the same thing for the other piece. I'll go to my unit circle, but this time I'm going to look for where x equals -1. Okay? Going back to my unit circle. Checking my x's. Aha, here's one at pi. And then I keep checking my x's. No other solution. So that's the only spot, right? So far, so good. Okay. Let's do another. So, is this one ready to go to the unit circle? No, what's wrong with it? I have an exponent and a coefficient, right? Which one do I get rid of first? You want to do the coefficient first. Remember, when you're solving, you want to go reverse order of operations. So you undo adding and subtracting, and then multiplying, dividing, and then exponents. It's the reverse order when solving. Everybody's good? So we divide both sides by 3. And then we'll square root both sides. What do we remember when we're doing this? Plus or minus. So far, so good. Now, remember, on the unit circle, tangent is y over x, right? So I don't really like the way that my answer is currently written as plus or minus square root of 1/3. I'm going to rewrite that so it's like number over number, so it's a little easier to deal with. Everybody's good? So I can write this as plus or minus. Well, when you take a square root of a fraction, that's the same thing as the square root of the numerator or a square root of the denominator. And I know the square root of 1 is just 1. Everybody okay to hear? The unfortunate part is if I go and I look on the unit circle for a place where y is 1 and x is square root 3, I don't see anything. Let's go show you guys. But what I do see is I see y, it can be 1 over 2, and x can be square root of 3 over 2. You guys see that? So my final piece here is I'll multiply the top and bottom of this by 1/2. So we're looking for a place where the, oops. Goodness gracious, Mr. Kulik. You just wrote it on the other page. So we're looking for a place where the x can be plus or minus square root 3 over 2, and the y can be plus or minus 1/2. Is everybody okay there? How I got to that, Gab?
Why did you use like pi over 6 like that? Those like on the unit circle. Why did you use that instead of like one where you could use like this one? Like how come you use this one instead of like? Does it matter?
Yes, it definitely matters, and it's because the top is the y. So I was looking for the place where the y coordinate had the 1 in it. Because the one you pointed to, why couldn't you use this one, has that 1 in the x spot.
Oh, okay.
Right? So you just have to be careful about that. All right, so let's go to the unit circle. So we're looking for places where the x has the square root of 3 over 2, either positive or negative. So there. Ugh. What did we just do here? There. And then there. So I have pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Is everybody okay? And notice that the y's also match in all those spaces. Is everybody okay with how I came up with the solutions there?
What is UC stuff?
Unit circle.
Oh.
So I'm just going to the unit circle. All right, let's look at the next one. Find the values of x on the interval from 0 to pi, or 0 to 2 pi. Okay, doing that again, fine. That satisfy the equation 2 cosine squared plus cosine x equals 1. Whoa, Mr. Kulik, slow down. I find like you've got two different trig, or we have two trig functions in this one. Haven't seen that before. When you look at that equation, 2 cosine squared plus cosine x equal to 1, what type of an equation, or what type of equation does this remind you of? We talked about them a whole bunch in Algebra 2 last year. Well, that's a factoring pattern.
The binomial?
So specifically, so that's fine. Polynomial's fine. Binomial's fine. Well, not really, because this has 3 terms. But you're in the right ballpark. What you're looking for is a quadratic with the Q. So if we rewrite this, where we just say, okay, let's pretend that cosine square or cosine x is like a y. We'd have something that actually is quadratic, right? You can see that now if I just replace my cosines with y's. Now you tell me, what are the different ways to solve a quadratic equation? We talked about a whole heap of methods last year. Somebody give me one method. Joey. Quadratic formula, that works. Sure. What else do we got? Well, factoring you would have used, right? What else? For example, one of those factoring methods you might have used was the difference of 2 squares, Abby. You were in the right ballpark. You're just playing the wrong game or something there. Well, what else? You can do graphing, right? Any equation you can solve via graphing with a calculator. You could have completing the square. You could do that. You can use a radical. Really, the only time you can use a radical, though, is if you only have a squared term, if you don't have a linear term, right? So if I look here, I have a linear term. So I know I can't use a radical to do this. Which one of these is probably the most tedious one to do? Okay. what I would say tied with graphing though is completing the square. You remember doing that where you have to like add, b over 2a to both sides and then like do some factoring thing and then square, it's kind of a hassle. So between the quadratic formula and factoring, let's say we use the quadratic formula. Both those methods, quadratic formula and factoring, will work here. What's the statement for the quadratic formula? What's the initial conditions that you have to have in order to apply it? Oh, come on, guys. If ax squared plus bx plus c equals 0, then x equals negative b plus or minus square root b squared minus 4ac all over 2a. Does that ring a bell? So the initial condition is this. Take a look at our quadratic equation. Do I have that? Daniel shakes his head no. Why not, Daniel? Because what's it equal to? 1. What's it supposed to be equal to? 0. Can we fix that? Yeah, what do we need to do? Subtract 1 from both sides, right? Everybody feel good there? All right. What's my A, B, and C then? What's A? Two. What's B? What's C? Good. So we can say then y equals negative 1 plus or minus square root 1 squared minus 4 times 2 times negative 1 all over 2 times 2. So far, so good? Okay. 1 squared is 1. What's 4 times 2 times negative 1? What? 4 times 2 times negative 1. Negative 8. And then what's 2 times 2? 4. Okay, what's 1 minus negative 8? Anybody can answer this. 1 minus negative 8. Nope, not negative 7. 9, right? Minus a negative means plus. What's the square root of 9? 3. Yes. Sure. What's negative 1 plus or minus 3? Is that just plus or minus 2? No, it is not. How do I do that? Yeah, I split it. So I do negative 1 plus 3, and then I do negative 1 minus 3. So my two answers are 1/2 and negative 1. Right? Everybody's good? So what we have then is y equals 1/2 or y equals negative 1. Are we done? No, why not? That's correct. We're not done. Remember, what is our original equation? This. What's the variable in that? X. What did we solve for? Y. So we have to substitute back in. We know that y is cosine x. So I go to my unit circle and look for where x is equal to 1/2. And then we'll go to our unit circle and look for where x is equal to -1. So let's start with the x equals 1/2. So there's one spot. There's the other spot. So pi over 3 and then 5 pi over 3. And then we'll go to the other one and look for where x is -1. Back to the unit circle. That happens just here at pi. Everybody cool? Why am I only looking at once around the unit circle? Remember in the problem, this was from 0 to 2 pi, right? So I only have to look once around the unit circle. Everybody's okay? That was different. I'd have a little bit different process at the beginning. We're going to see that here coming up in the next two examples. So our next one says, find all the values of x that satisfy the equation 2 tan x sine x equals tan x. First observation, what interval does it tell me to solve over? It doesn't, right? That means I'm going to have to write my answers like in the infinitely many situation. So I'm going to have to write them like answer and everything coterminal to it. I'm going to have to use that notation. Does everybody see that? The second thing I notice here is that I have two different trig functions in my equation. So when I see that, one of two things is going to have to happen. Okay? When I see two different trig functions in the same equation, one of two different things has to happen. One, the first option is I can try to use some identity or identities to rewrite them so they're all the same trig function. Now, do I have a way to write tangent so that it has only sine in it? No, right? Tangent could be 1 over cotangent. That doesn't help. Sine over cosine. That doesn't help because it has a cosine in it. Or secant over cosecant. That doesn't help. The other option would be, can I rewrite sine so that it has only tangent in it? No. I can write sine as 1 over cosecant, but that doesn't help. So an identity is not going to get me there. Everybody see? That's all I'm doing to check is see, can I make them all the same kind of trig function? So instead, what I'm going to have to do is I'm going to have to try to do some kind of factoring. So I'm going to move everything onto one side. So I'll subtract tan x from both sides. So that it's equal to 0. Whenever I'm about to do factoring, I have to be equal to 0 because I'm going to need to apply the zero product property at some point. So my equation has to equal 0. It's got to be the very first step whenever I'm solving by factoring is to make it equal to 0. So far, so good. Now, do you see any squareds anywhere in here? No. So this will not factor like a quadratic. So it's going to be the easier kind of factoring that you learned in like pre-algebra that you've all forgotten by now. It's called a least common multiple. So if I look at the first term and then I look at the second term, do you see anything in common between the two? the tan x, right? So I can factor a tan x off. When I do that, what does 2 tan x sine x become? It becomes 2 sine x. Remember that when we're factoring, really what we're doing is dividing. And what does tan become then? 1. Everybody okay there? Now look at what's happened with our factoring. This factor has only tangents in it. This factor has only sines in it. By factoring, we've effectively separated these two different trig functions. You guys see that? So now we can apply the zero product property and split this into 2 separate equations. Is everybody happy with that? Looks familiar, right? Just like solving by factoring last year in Algebra 2. So here the tangent is all by itself, so I'm ready to go to the unit circle. So on the unit circle, tangent is y over x. If y over x is equal to 0, all that's saying is that y equals 0 and x doesn't, right? Because 0 over 0 is undefined, right? That's actually a specific thing. We call it indeterminate. Is even different than really what undefined means. So I'm just going to go to my unit circle now and look for the places where y is 0 and just make sure that x also isn't 0 there. So y is 0, x isn't, so 0. Chugging along, looking at my y's. Here's another one. And then I'm back over here. So my solution should be 0 and pi, right? Mm-hmm. But remember, this was the infinitely many solution situation. So we have those two. Everybody's okay there? But we're not done. Why aren't we done? We still have the other half to do, right? 2 sine x minus 1 equals 0. What do we need to do to solve that equation? What should we start by doing? Add 1 to both sides, and then? Well, we got to divide by 2, and then we're going to go to the unit circle and look for where y equals 1/2. Everybody good? Go back to my unit circle, scrolly, scrolly, scrolly. So I have here at pi over 6, and here at 5 pi over 6, and no other place where y is 1/2, so those will be my 2 that I need. So again, we want those and then everything coterminal to them. All right. I want to point out one thing to you guys here. So the answer as we've written it is correct. Okay? However, if you go and you check, you look at your solutions in the back of the book, this is not how the back of the book is going to write it. Let's think about what solutions are here that I've circled in green. So for example, the first piece would include 0, 2 pi, 4 pi, 6 pi, 8 pi, etc. Correct? The second piece includes 1 pi, 3 pi, 5 pi, 7 pi, etc. Correct? If we take those together, we're including 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, etc. Correct? So the way that the back of the book would write this is just pi k, where pi is an integer. You do not have to do that, but that's less writing. If you're checking in the back, that is how they will do it. Okay? Is it okay to write your answers the way we circled them in red? Yes. I will not mark it wrong. They are equivalent statements. They are both correct. But the person writing a textbook is going to conserve symbols whenever possible. Okay? If your answer doesn't match the back of the textbooks, just check to make sure they don't mean the same thing, right? To make sure there's actually a mistake there. Because very likely you could be a situation where you've written it in red, the answer is the one given in green, but they mean the same thing, right? Just like enumerate some of the answers and make sure that it's like, oh, okay, these two are just saying the same thing. I'm good. Is everybody okay there? Just to point that out. All right, folks, hang in there. I got one more example, and then we can be donezos. Yay! Find all the values of x from, negative 4 pi to 2 pi. That's a big interval, Mr. Kulik. How big is that? That's 6 pi long, right? That satisfies the equation sine squared equals sine x. Okay. So let's just stop for a moment and kind of talk about what I'm seeing and what it means to me. So this tells me I'm going to write the infinite solution and then use k's, input values for k to keep generating solutions until I've exhausted all the possibilities. Everybody's okay with that? We'll do it as an example. I'll be really explicit and write everything out, even though in practice I would encourage you to do it in your head because it can be a lot of writing. What does this piece tell me? What type of equation do I have? What exponent do you see here? Squared, degree 2. That means it's quadratic. Now, what do you notice that's different about this quadratic equation versus the previous one? Well, there's no constant term, right? If I go back to this one, we're at 2 cosine squared plus cosine equals 1. There's no constant term in my equation that I have down below, sine squared equals sine. Everybody see that? If there's no constant term, that's great news. It means that I can just factor this using a least common multiple, just like I did the previous one. So I'll move the sign over to the other side so it's equal to 0. And then the LCM, what's the least common multiple between sine squared and sine x? Sine x, right? So when I factor sine x out of sine squared, I'm left with sine x. And when I factor sine squared out of sine squared, I get, or sine x out of sine x, 1. So I use my zero product property and break that into two equations. So the first one's ready to go. I'm just going to go to the unit circle and look for where y equals 0. So go back. So it happens here at 0, and then here again at pi, right? Okay. But remember, because we have so many solutions that we're going to be looking for, I'm going to start with the infinite solution. And now I'm going to start enumerating solutions. So if k equals 1 or k equals 0, I get 0 for my one solution. And I get pi for the other, right? Are both of those between negative 4 pi and 2 pi? Yes. So I'm going to keep both of those. Now I'm going to try the next biggest k. So let's say if k equals 1. So 0 plus 2 pi times 1, well, that's just 2 pi. And then pi plus 2 pi times 1, well, that's 3 pi. Well, 3 pi is too big, right? So that one doesn't count. Should I count 2 pi? Does the bracket mean I count it or not? The bracket means it is included, so I'm going to count that as well. So because I found the very tippy top, right? It's either I'm right at the biggest answer I could possibly have, or it's too big. I know I've done as big a k as I need. Now I'm going to switch and start checking the negatives because I still have negative answers that are possible. So I'll start with k equals negative 1. So I get negative 2 pi and then negative 1 pi. Both of those are okay. They're between 4 pi and 2, or negative 4 pi and 2 pi. Okay, so we'll keep getting smaller. So there I have negative 4 pi and negative 3 pi. Again, negative 4 pi counts because it's a bracket. Negative 3 pi is in between. And because I found the very tippy top of my, or very, I guess, bottomest bottom of the interval, I know I'm done here also. So my solution should be negative 4 pi, negative 3 pi, negative 2 pi, negative pi, 0 pi, and 2 pi. Everybody okay with that? Am I done? No, I still had another equation that I have to solve for. Notice that I just ordered these from smallest to biggest. You don't have to do that. That's the way the answers in the back of the book will probably be arranged, though. All right, so if I go to the other one, sine x minus 1 equals 0, we'll just add 1 to both sides. And then we'll go to the unit circle where y equals 1. All right, let's go look there. So I have here at pi over 2, that's the only spot. Oh, thank goodness, Mr. Kulik. So I have x equals pi over 2 plus 2 pi k. So we'll start at k equals 0. So that gives me pi over 2. Then we'll do k equals 1. Since that worked, we'll just keep getting bigger. You could get smaller first also. All right. Pi over 2 plus 2 pi. What do I need to have? To add them together. Common denominator. I'm going to do this all in my head. Is that okay with you guys? Okay, you all said yes. So when you ask me a minute where like 5 over 2 pi comes from, I'm going to like bang my head on the table and be like, we just talked about this. What were you doing? Just to give you a heads up. So that's going to be 5 pi over 2. Or if I think about it, it's 2.5 pi, right? If I add 2 pi to that, what's going to happen? Too big, right? Because again, we're going from negative 4 pi up to 2 pi, right? This is already too big. So we're done there. If I do k equals negative 1, it's going to be negative 3 pi over 2, or negative 1.5 pi. That's good, right? And if I say k equals negative 2, it's pi over 2 plus 2 pi times negative 2. That's going to be negative 7 pi over 2, or negative 3.5 pi. That's still good, but if I subtract another 2 pi from that, it's definitely going to be too small, right? So those are my other solutions. Oops. Write them from small to big. You don't have to do that. It's the math teacher in me. So all those are my entire solution set, right? Now in practice, I'm not going to write this stuff down, right? What I'm doing is I'm just going to look at this and go, okay, 0, that fits. If I add 2 pi to that, that fits. If I add 2 pi again, that doesn't fit. If I subtract 2 pi, that fits. If I subtract 2 pi again, that fits. If I subtract 2 pi again, that doesn't. Done. Go to the next one. I have pi, that fits. Add 2 pi to that, that doesn't fit. If I subtract 2 pi from that, that fits. If I subtract 2 pi from that, that fits. If I subtract 2 pi again, too small, done. Right? Like I'm not gonna write all this gobbledygook down. I'm just gonna just keep adding or subtracting 2 pi from that base answer until the things don't work. And then I'll move on to the next answer and just add or subtract 2 pi until things don't fit. And then move on to the next, you know what I'm saying? Like, I wrote all that stuff down so you could see how the infinite solution was helping me and like what I'm really doing. But like, I'm not writing all this down by hand. I'm doing it in my head because all we're talking about is like adding and subtracting 2 pi's. You know what I'm saying? Does that feel okay? All right. So for your homework, so what I want you guys to do, let's do, say, 15 to 33. We'll just do the oddsies. And then I would like you to do all of 43 through 46. But keep in mind here that each of these problems has like an A, B, C, D to it, where you're solving over different intervals. Now, I tried to arrange this so it's not like really 4 problems for each. Because once you found your answers for 0 to 2 pi, that automatically gives you your infinite solution. You just have to put a plus 2 pi k at the end of it, right? And once you have that, you can generate easily the answers from, well, you already have the answers from 0 to 2 pi, so you just need to generate the answers from negative 2 pi to 0. Basically, k is negative 1. And then once you have those, well, you already have the answers from negative 2 pi to positive 2 pi. So you just need to pick the ones out of there that are between negative pi to 2 pi, and then you just generate the answers from 2 pi to 4 pi, are the extra ones. So like I tried to pick intervals where the previous problem is going to basically give you answers to the next part. So you don't have to do like all of it fresh. You can just use the previous answers to build out most of your solution set and maybe add a couple more or drop a couple. Is everybody okay with what I'm asking for here? Okay. Next class will be the review day. So we'll have the half sheet due next class. That said, I want to point out that if you look at the review, the test format is on actually the review guide here. And I did that because the format here is a little bit different than the typical test. So there's going to be 10 total questions. You only have to finish 8 of them. So there's going to be 4 questions that are required, the first 4 questions. 2 of them will be simplify, like you did in the homework quiz or the first homework sets. And the second 2 questions will be solving, just like we just got done doing. Then there'll be 6 trig identities. You get to pick any 4 to do. So you don't have to do all of them. You have some freedom there to avoid the ones like, I don't know what to do with this. Like I just throw up my hands at it and be like, whatever, I can't figure this out. So you can avoid a couple. Does that feel okay? So again, as you're building out your note card, keep in mind the format for the test. You don't need any identities on there. I will give you the same identity sheet that I printed for you earlier. That'll be on your test. So you don't need that. Everybody okay? Okay. Questions for me about anything we've done or talked about so far? Okie dokie. Very good. I'm going to stop the recording. You guys can spend the last 20 minutes or so of class starting on your homeworks.